All right, now that we have the HDL code from Simulink and or MATLAB, we can begin the validation process. So here you can see the MATLAB or Simulink generated HDL code for the polyphase interpolation filter. We're going to build a test bench in order to test this. Now, Simulink and MATLAB both can build test benches, but I find that their test benches can be a bit cumbersome. The one advantage to building the test bench, though, is that they do generate input and output vectors that you can use to validate your Verilog. So here's the test bench that I built. We have 2 clock periods because we have an interpolation filter. The interpolation filter is ostensibly trying to interpolate from 400 megahertz up to 1600 megahertz. But I want to make sure that we can close timing up to a frequency of 2 gigahertz. So I'm using an input period of 2000 picoseconds, which corresponds to an input frequency of 500 megahertz, and I am using an output period of 500 picoseconds corresponding to an output frequency of 2 gigahertz. Here you can see I set up the signals, so we have a clock, a reset, and enable, the input vectors, the clock enable output, and the output vectors. I have some file handling variables that are used because I'm going to load these data files into the system. I instantiate the filter. I create a clock. I initiate a reset and then an enable. And finally, I load the input vectors and clock them in to the system. To test the output vectors, I set up another procedure that is going to clock in the output data, the expected output data into a register. That happens on the output clock period. And then we test mismatch between the real vector and the imaginary vector. If there is a mismatch between the 2 vectors, then we will find, then it will output there's a mismatch at a particular time in the simulation. Now, one thing you'll note here is that I do have a static offset that I add. This has to do with the delay between the input being valid and the output being valid. All right, so let's run the simulation. Now, I'm going to do this in iVerilog. So, using iVerilog, and you can find a tutorial on setting up iVerilog at this website. I'll link to it in the video. So here we run iVerilog using the command iVerilog. We send it to an output int filter wave, and we load all of the necessary Verilog files at this time. If we run this command, we shouldn't get any errors. We didn't. So now we're going to run the actual simulation. And what you'll find when we run the simulation is I've turned off the monitor that would be outputting a display just to make sure that the simulation's running. But if you want, you can re-enable something like that. I'm going to pause the simulation after some period of time. It'll tell you how long it's run. And now we can go to the MOBA Xterm here, open up Windows System for Linux and MOBA Xterm, and this is going to allow us to forward X to the display. So here I'm going to open up GTKWave using the command GTKWave with the waveform file that we create. And we're going to look at the output vector and input vector. I'm going to zoom in, and ideally we'll see that the output vector the expected vector matches the output vector, and the expected vector for the real part matches the output vector for the real part. And you can see that they do match. Now, this isn't a formal verification of functionality. This just says, more or less that the Verilog is producing the expected output. Now, we can look at other waveforms here. We can look at the clock. We can look at the reset. We can go into submodules if we want and look at various functions inside of the submodules. If we want, this is some random coefficient. We can find different things if we were really trying to debug this. All right, so with that, we've now validated that our Verilog does indeed produce the expected results that we would expect if the filter is working. And so with that, we're also ready to move on to the synthesis phase, and we'll do that in the upcoming videos.